Every day, millions of people ride trains without a second thought. Passengers chat, read, or doze off as massive steel machines weighing hundreds of tons hurtle toward each other on the same tracks, somehow never colliding. They trust the system and rarely think about what's keeping them safe. But what if I told you that the technology preventing catastrophic train collisions has been evolving for nearly 200 years? Statistically, trains are among the safest forms of transportation, with accident rates far lower than cars or buses. Yet they travel at incredible speeds, carry thousands of passengers, and unlike cars, can't swerve to avoid obstacles. But here's the strange part. Even as trains have evolved from steam-powered machines to high-speed electric marvels, the fundamental principle keeping them safe hasn't changed since the 1830s. So how do railways manage to run thousands of trains daily with such remarkable safety records? And what makes railway signaling so uniquely effective at preventing disasters? To answer that, we need to look at where it all started. In the early 1800s, the world's first railways were remarkably simple. Most lines connected just 2 points, perhaps a mine and a port, or 2 neighboring towns. With only one train operating on a line at a time, safety wasn't complicated. But as railways expanded and demand grew, companies needed to run more than one train on the same tracks. That created an obvious problem. Without a way to keep trains separated, collisions were inevitable. The earliest solution was surprisingly low-tech. Railway companies stationed men called policemen or flagmen along the tracks. These human signals used colored flags to control train movements. Red meant stop, yellow meant caution, and green meant proceed. But these flagmen weren't making their decisions based on where other trains were located. Instead, they used something called the time interval system. A policeman would check his watch when a train passed and then use different flags based on how much time had elapsed. If less than 5 minutes had passed since the previous train, he'd show a red flag to stop the next train. Between 5 and 10 minutes, he'd wave a yellow flag for caution. Only after 10 minutes would he show a green flag, allowing the next train to proceed at full speed. The problem was obvious. These flagmen had no way to know if the previous train had actually cleared the next section. What if a train had broken down just around the bend? The flagmen wouldn't know, and the next train might crash straight into it. And these weren't theoretical concerns. Trains require enormous distances to stop, around 700 to 1,500 meters depending on speed and weight. By the time a driver spotted a stalled train ahead, it was often too late to avoid a collision. The inevitable happened frequently. Rear-end collisions were common, and passengers faced real risks every time they boarded. This crude time interval approach also severely limited capacity. With 10-minute gaps between trains, railways could only run 6 trains per hour on any given track. As demand for rail travel exploded, this system simply couldn't keep up. By the 1840s, it was clear that something needed to change. The breakthrough came with the introduction of fixed track signals and a new concept, the block system. Instead of timing gaps between trains, railways divided their tracks into sections called blocks. The golden rule emerged. Only one train could occupy a block at any time. The first fixed signals began appearing on British railways in the late 1830s, mechanical arms called semaphores that pivoted to different positions. The London and Croydon Railway was among the pioneers implementing these systems. These signals were physically operated by signalmen pulling levers connected to the semaphores through a complex system of wires and pulleys. But there was still a problem. How could signalmen know when a train had cleared their block and entered the next one? The answer came with the invention of the telegraph. Suddenly, signalmen could communicate with each other instantly. When a train left one block, the signalman could telegraph ahead to the next block, letting his colleague know a train was coming. Once the train had completely passed the second block, that signalman would telegraph back confirming the block was clear. This was revolutionary. For the first time, train movements were based on actual location, not arbitrary time intervals. But there was still a critical issue: human error. If signalmen made mistakes in their communications or forgot to set signals correctly, disasters could still happen. Interlocking systems have come a long way too. What began with mechanical levers physically preventing conflicting movements has evolved into sophisticated software running on redundant computer systems. Modern computer-based interlocking, CBI, can manage complex junctions with hundreds of possible routes. constantly analyzing every movement to prevent conflicts. For safety-critical systems like these, railways don't just rely on a single computer. Instead, they use 2 out of 3, or even 2 out of 4 voting systems, where multiple computers independently calculate what should happen next. Only if the majority agree is the command executed. If there's disagreement, the system defaults to the safest state, usually stopping the trains. By the 1860s, these technologies came together in the form of signal boxes, small buildings housing levers, controlling signals, and points, or switches as they're called in America. A trained signalman could now safely route multiple trains through complex junctions without risking collisions. But as trains got faster, a new problem emerged. Drivers needed more warning about signals ahead, especially when approaching a stop signal. The solution was to classify signals as either home or distant. Home signals were placed at the entrance to a block and could show stop or proceed. Distant signals were placed further back, usually around 1,000 meters before a home signal, giving drivers advance warning about the home signal's status. To differentiate these signals, color became important. Red always meant stop, green meant proceed, and yellow was introduced as the color for caution, typically shown on distant signals when the upcoming home signal was at stop. These mechanical signals served railways well, but they had limitations. They were difficult to see at night, even with oil lamps attached, required significant maintenance, and still relied heavily on human operation. When fog rolled in, a common occurrence in Britain where many signal advancements were pioneered, mechanical signals became nearly invisible. Railway companies tried various solutions, including placing small explosive charges called detonators on the tracks that would make a loud bang when run over, alerting drivers to signals they couldn't see. But these were temporary fixes to a fundamental problem. The next big leap came with the introduction of electric track circuits in the 1870s. Invented by American William Robinson in 1872, track circuits automatically detected when a train was in a block. Here's how they worked. A small electrical current runs through both rails in a block. The rails are insulated from adjacent blocks, and a relay at the far end connects to both rails. When no train is present, the current flows through the rails to the relay, which completes a circuit keeping the signal green. But when a train enters the block, its metal wheels and axles create a short circuit between the rails. This cuts the current to the relay, automatically turning the signal red. This was revolutionary. Blocks could now protect themselves automatically. If a train stopped anywhere in a block, the signal would stay red until it moved out, regardless of what the signalman did. As electric lighting became common in the early 20th century, railways began replacing mechanical semaphores with color light signals. These were more visible in all weather conditions, required less maintenance, and could be automatically controlled by track circuits. The typical 3-aspect signal system was born: red for stop, yellow for caution, prepare to stop at the next signal, and green for proceed. But signal visibility remained an issue as train speeds increased. By the mid-20th century, some trains were moving so fast that drivers had trouble seeing and responding to trackside signals in time. This wasn't just about comfort or convenience. It was a matter of life and death. The UK experienced this firsthand in the 1952 Harrow and Wealdstone disaster, where a fast express train crashed into the back of another train during foggy conditions. Minutes later, a third train crashed into the wreckage. The triple collision killed 112 people and injured nearly 340 more. One key factor: the driver of the express train had missed a caution signal in the fog. Events like these pushed railways worldwide to develop better ways to communicate with drivers directly, regardless of weather or visibility conditions. The next big leap came with automatic train protection systems, or ATP. While early concepts of train protection existed as far back as the 1930s in countries like Germany, it was the 1960s that marked more widespread development and implementation, especially as high-speed rail began to emerge. A TP monitors a train's speed and automatically applies the brakes if the driver fails to respond to signals or exceeds speed limits. The key principle behind ATP is the braking curve concept, a mathematical model that calculates exactly how fast a train can safely travel at any point, ensuring it can stop before any danger point. but even ATP systems had limitations as trains got faster. Signal visibility becomes increasingly critical at speeds of 200 to 250 kilometers per hour, varying with signal placement and weather conditions. As high-speed rail pushed beyond these thresholds, it became clear that trackside signals were no longer sufficient, regardless of their design. This led to cab signaling, moving the signals from beside the track directly into the driver's cabin. Instead of looking out the window for signals, drivers now check displays showing the status of signals ahead. This information is transmitted to the train either through the rails or via radio signals. As we entered the digital age, signaling took another leap forward with the concept of moving blocks. Traditional block systems divide the track into fixed sections, but with moving blocks, the safe zone around each train is calculated dynamically based on the train's speed, weight, and braking capability. Think of it like cars on a highway. Instead of dividing the highway into fixed sections and allowing only one car per section, moving blocks allow trains to run as close together as their stopping distances safely permit, significantly increasing capacity without compromising safety. These modern systems rely on precise knowledge of each train's location, which comes from a combination of trackside sensors, GPS, and onboard computers. The shift to moving blocks wasn't just a technical evolution. It represented a fundamental rethinking of how railways manage safety. Instead of the Victorian-era concept of blocks with fixed boundaries, engineers began to think in terms of dynamic safety envelopes that moved with each train. Early tests of moving block concepts faced significant challenges. Computing power was initially insufficient to handle the complex calculations needed in real time. Communication systems weren't reliable enough to guarantee uninterrupted data flow. And perhaps most importantly, engineers and regulators needed to develop new safety frameworks. After all, they were replacing a system that had worked reliably for over a century. Today, the most advanced systems don't use trackside signals at all. The European Train Control System, ETCS, is one example, part of a broader effort to standardize signaling across Europe's railways. ETCS Level 3, which uses full moving block operation with all communication happening via radio between trains and control centers, has been piloted in countries like Sweden and Germany. However, it's not yet widely implemented in full operational service due to reliability challenges and the need for robust fallback safety systems. Most high-speed lines currently operate with ETCS Level 2, which still relies on some fixed block principles. Similarly, urban metro systems often use communications-based train control, CBTC, a technology that can, under optimal conditions, allow metro trains to run as close as 90 seconds apart, essential for busy urban networks. However, this spacing isn't guaranteed in all conditions and varies between systems. Some CBTC systems even allow completely automatic train operation with no driver needed. But with all this technology, the fundamental principle remains unchanged: keeping trains safely separated. So how do different countries approach railway signaling? Britain, where railways began, has one of the most complex signal systems, reflecting the gradual evolution of its network. You'll still find some mechanical semaphore signals on rural lines, alongside the most modern computer-controlled systems in urban areas. Germany developed its own Elsa-B system for high-speed lines that uses inductive loops between the rails to communicate with trains at speeds up to 300 kilometers per hour. They're now transitioning to the European standard ETCS. France pioneered high-speed rail with the TGV, developing advanced cab signaling systems that eliminated trackside signals entirely on high-speed lines, allowing safe operation at speeds over 300 kilometers per hour. Japan, with its Shinkansen network, developed entirely separate tracks for high-speed trains with its own digital ATC system. This separation from conventional lines is one reason why the Shinkansen has never had a fatal accident due to collision or derailment in over 50 years of operation. South Korea is testing LTER, a railway version of the 4G mobile technology we use in our phones, as a platform for next-generation signaling. Some researchers are even exploring how 5G might revolutionize train control systems. But even as technology advances, the challenges remain. Modern signaling systems face new threats like cybersecurity risks. A hacked signaling system could potentially cause catastrophic accidents, so robust protection is essential. This isn't a theoretical concern. In 2008, a teenager in Lodz, Poland, used a modified TV remote to change track switches, causing a tram derailment that injured 12 people. While not a sophisticated cyber attack, it demonstrated the vulnerability of rail systems to external interference. Since then, railways worldwide have invested heavily in security measures to prevent such incidents. Train detection still isn't perfect either. Track circuits can fail during floods or when leaves fall on the tracks, creating an insulating layer. Axle counters can sometimes miscount, especially when trains change formation. Despite these challenges, the evolution of railway signaling represents one of humanity's most successful safety systems. From human flagmen with stopwatches to computerized moving blocks, each innovation has built upon the last, always preserving the core principle: only one train in one section at one time. This steady progression has made trains remarkably safe. In the European Union, there are typically fewer than 30 passenger fatalities per year across all railways, despite carrying over 8 billion passengers annually. In Japan, the Shinkansen has moved over 10 billion passengers without a single fatality from operational accidents. As railways face growing demand and the push for more sustainable transportation, signaling technology continues to evolve. Future systems might use artificial intelligence to predict maintenance needs before failures occur or optimize train movements for energy efficiency. But whatever technologies emerge, they'll all be built on that same fundamental principle established nearly 200 years ago: keeping trains safely separated while moving them as efficiently as possible. The next time you're on a train speeding through the countryside, glance out at those colored signals flashing by. They're the visible tip of an invisible system that's been evolving for nearly 2 centuries, silently keeping you safe with every kilometer traveled.